Okay, let's see, let me remind you, I put the graded second lab report on the table outside my office. I scanned those before I did it, but I failed to do it. I forgot for the first one. These scans will be useful for me, as I mentioned in an email message to you, for next quarter with the distance learning students. So 2 groups still need to do it. Faisal, Sean, Daniel, Kevin, Steve.
I have.
Okay, so you guys still have. So just scan them and email them to me. That'll be great. Yeah, I appreciate that. Sorry, I should have done it. I'll do it from now on. Okay, so today we're going to finish chapter 5. We're talking about the thickness vibrator. And I think we're going to have time to get into even though it's not on the syllabus, I think we'll have time to get in to do the first problem on the problem set, which is good because looks like it's a little longer, this problem set tomorrow. So that'll be good, I think, to do that. And the first problem's not too bad. Okay, so the thickness vibrator we talked about a long time ago, whenever that was. What's happening here is we're making the assumption that the frequency is sufficiently high such that there's no bulging and contracting. You drive it this way, it expands and contracts that way, but it's negligible that way. It's unilateral compression and extension. And probably the main reason that Brian did that was because it forces us to look into, it's very natural here to change the independent variables. It makes it a lot easier to solve. So I think that's probably why he did it. It's an example of where we shift our usual T and E as independent variables. It's the natural variables here are strain and displacement. So we did that, we went through and we did the free case where the forces are 0 here. So this would be, in a practical sense, this is in air. If this is really intended for water. So air is approximately a vacuum compared to water. So these forces will be negligible. So the next thing we want to do is, and we won't go through the math here. We've done this several times before. We've gone through this path of no force, and then we put the force in. So let me just briefly mention, it's the same idea. We write down we have a standing wave. As we did in the free case, we have a standing wave solution in this direction here, a general standing wave. And it's in terms of up and down traveling or right and left coefficients, it's in terms of those amplitudes. What we do when you put a drive in is we go to our standard independent variables. We express A and B now in terms of those displacements. This is just like we did several times before. And then we impose boundary conditions on the transducer here in terms of general force. So before we had, the right-hand sides were 0 here because we had no forces. So we're generalizing. But you do have to go through, we took a different route, we took a different approach here, but now with the force being in here, we need to express this in terms of velocities at the ends. So now you just, from the piezoelectric relationships, you can get expressions. If you, in canonical form, it would be the forces in terms of the velocities. That's the canonical. Remember, first thing in chapter 2. And you get these expressions, and they're somewhat lengthy here, I seem to recall. But we don't care, right? Because they're all embodied in this equivalent circuit. You can show that this is the equivalent circuit. So once we've got this, we're off and running. We don't really need those equations. We can generate them from here very, very easily. This summarizes all the information. And we'll look at an example, at the end of the lecture, we'll look at an example near the end of the use of the equivalent circuit here. Okay, so let me see if I've got everything here. Well, we mentioned this last time. You'll notice there's this weird minus capacitance here. We've actually encountered this before if you look back, as I mentioned, I think, in the last lecture. If you go back and look at Chapter 2, those 5 equivalent circuits, we had this. This occurred in one of them with the transformer. There was another one. There was a negative impedance on the right-hand side. So I have to admit, I don't have a physical feel for how this comes about here. Transducer people probably do, but it's there. And again, this is the purpose of this is for us to be able to handle the transducer, and we don't need to construct this, right? It's the piezo. It's already, in a sense, it's already constructed. It's the thickness vibrator here. So you just treat this as an abstract sense. The voltage drop here is the opposite of what you'd expect if it were a real capacitor. Okay. All right. Now, we have a little bit of a problem here. This is what we've been using in the lab, right? So I think we confirmed that for the ring. God, I've already forgotten. I think we did confirm this for the expansion ring, right? And we'll do a problem on that, hopefully, this hour. But this doesn't look like this. So do we have a problem here? Is this just a special case for this particular geometry of an expanding ring? No, fortunately, the answer is no. And the answer is near resonance. And by resonance here we mean motional resonance, mechanical resonance. This is going to behave like that, which is what I think you'd physically expect that, but transduction is a difficult subject, right? So you want to be careful about saying, oh yeah, it's physically reasonable. It makes us feel better, but you want to be careful. So we're going to look at this right now. Look at this circuit near resonance. And the idea is this. The idea is, let me hold on. We're going to consider, for simplicity, we're going to consider free, no force, okay? All right, so you can see here that I think I drew these in here to Brian's diagram. You see that these have been shorted, okay? It's force-free. So we want to show that near resonance, that this behaves like that. What do we mean by that? Well, what we mean is we can find values of the elements here in terms of these values such that this approximately behaves like that. So let's write down the motional impedance. We're just focusing on the mechanicals. That's all we need to do here, focus on the mechanical side. Let's write down the motional impedance of this exactly. And here it is. You can see we have these two. You can bring in, by symmetry here, these are the same voltage. You can connect those two terminals. Right? So you see that these are in parallel. So the equivalent impedance there is going to be 1/2, and then it's in series with this. And then, what's happened here? Why is this here? You're used to this. You should be used to this by now. We've removed the transformer. Okay? Removing the transformer makes these elements, which is fully an electrical circuit now. These have electrical values. So here's the motional impedance. But remember, it's a capital M, so it's electrical. Okay, so that's exact, right? We'll substitute, if you go back and look at the diagram, you'll see that relationships for these impedances up here and other quantities are written down. So here they are. Z1 happens to be this, Z2 is this. This is in general for any standing wave in there. You can tell standing wave nature here, where Z0 is equal to this, okay, in terms of fundamental parameters. So I've substituted these expressions into here. We'll hold off on substituting the Z naught. Okay. Now the first thing to notice here is that we've got there's no damping here. You know, these are, these look like resistors. These are impedances. And because we don't have any damping in the theory, this makes it easier here. The conclusion here is going to hold with damping. It's probably as long as it's not too large, is my guess. I don't know. But because there's no damping, evidently this is going to have to be 0. The motional resistance here is going to have to be 0. So the motional impedance here is going to have to be just this. It's going to be a reactance. It's going to be that for our simple circuit. So here's the idea. Can we make this, well, here it is. We make this equal to that. Can we set those two things equal? Yeah, we can set them equal. And you'll notice that they're both imagined. It's one equation. It's not two equations. It's not complex because the i's drop out. It's just one real equation is what we end up with. We have one equation. How many unknowns do we have? Anybody? I know it's 8 a.m., long holiday weekend. 2, right? Yeah, we need to determine these two things. And you know, it's not. I should point out. I don't know if I pointed out in the notes. Hold on. So we have an overabundance of constants here, but we'll take advantage of that in a moment. But it's not obvious that you can do this. I just want to point, just because you have, okay, maybe I better stipulate. So we have, here's the idea. We have, we can think of frequency this way, okay? And we have these two functions. And here's the, here's resonance. We can demand that they're the same here, all right? But we can do more. Because we have one equation and two unknowns, we can make the next step, which is what? We want this to be valid in a region. So what would you do? Well, you demand that not only do they agree here, but the slopes are the same too. So they have, not only do they have the same value here, their slopes are the same. So it would look something like this. And I don't know, I'm just, you know, just guessing here. This is just kind of abstract, okay? So we can, that didn't look too good. So I can demand here that not only do they have the same value, but they have the same slope. And this is nice, of course, because we want this to be valid in a region here. So we have the freedom to do that, but it's not clear that it's going to work. Just because you have two equations, we set not only the values here, we set the slopes the same too, okay? So they oscillate, whatever the word is here, right? It's not clear that a solution exists. Because these aren't linear. You see, they're not linear. They're not going to be linear equations. This is downstairs. So we're not guaranteed a solution here. But it turns out it can be done, okay? And I think I checked this. What we're going to do here is focus on the fundamental mode, the half wavelength resonance. Okay? So it's the lowest mode here. That means K times L hold on, why did I say shouldn't it be T? Okay, it looks like it's a minor. We're doing this, right? Okay, we want to look at the fundamental mode here. So it should be T, not L, looks like. Okay, I'll check that, but I'm pretty sure that's a mistake. But I have L's in these, I'm lost. I've got L's. I must have copied equations. Okay, I think I know what happened, yeah. Okay, so this is the tip of an iceberg here. I think these should be T's. I'm gonna have to check this. I probably copied these from some other problem and I failed to change the T. So I'll check into this, but I'm pretty sure that's the problem. Okay, so when you do that, you have two equations and two unknowns. It turns out you can't find a solution. We're focusing on the fundamental, and this is what you get for those parameters of the simplified circuit, the motional values. And it's not surprising this is proportional to the mass, okay? Because inductive is associated with inertia, and this is with the capacitance with the compliance. Now, I remember being a little concerned about this, if I did it right, and I can't remember what's in the book. So I checked it. A check here is that we know what the resonant frequency has to be in terms of our simple circuit. It's got to be 1 over the square root of, it's got to be. So if you plug these expressions in, you'll find that it is equivalent. And again, that should be a T, I think. It does give you the right answer. So that's good. Okay, so that's really useful. This is what we're now starting to see why we've been able to get away with. It's reasonable physically, but you know, there's no substitute for proper treatment when you can do it. Okay, any questions about that? Finally, even though this says vibrators, or projector, often called projectors or emitters, unemitters. Brian snuck in a hydrophone example here, okay? So we're going to look at that right now. So the thickness vibrator is now going to be, it's reversible, it's reciprocal is the technical name. So we're going to think of it as a hydrophone. You can operate it as a hydrophone to pick up sound. Now we're going to make the standard assumption, which is almost always true in sonar, for an element, not necessarily for an array of elements that some of you are familiar with, right? On submarines, for example, I'm sure that. But just an element. Usually the wavelength of sound is substantially greater than the size of the element. It's almost always or almost always true. So we're going to make that assumption here. And that makes life easier because I've got my thickness vibrator here. Sound is coming in. What's going to be, at any instant of time, what's going to be the pressure here compared to the pressure there? Same, because the wavelength is large compared to the thickness. So technically, the pressure is a little different. There's going to be a little phase difference. You know, they'll be out of phase and, slightly, but it's negligible. So that's nice, okay? Now, it's usually a nice thing, but it causes trouble here, is that if the wavelength is large in water, what's it going to be in the solid? Is it going to be large in the solid, or what do you guess? What's your? Usually the speed of sound in solids is greater than the speed of sound in liquids, right, in water, and it's true for ceramics. So the wavelength is larger here. If large wavelength here, inside here, it's going to be even larger because the speed is greater. All right? So unfortunately, we just violated our assumption. Remember, we're assuming in the thickness vibrator, however it's oriented, we're assuming that it's high frequency, so we don't have any Young's modulus, Poisson's ratio activity there. You know, it's unilateral compression expansion. When you drive this thing with sound at a low frequency, it's going to be bulging. It's not going to be unilateral. So we have a little bit of a problem here. So what we're going to do is just ignore that. We're just going to go ahead and use our theory, but understand that there's a severe limitation here. You know, you'd have to, you're not doing the right, the solution that we have, well, the information that we have for the thickness vibrator is the opposite frequency limit from what we're doing here. But we'll just go ahead and follow the book, and it's instructive to come up with the answer, but you have to remember that it's not right, okay? It can be done correctly, but I think it's better just to follow the book. So that's what I'm saying here. Oh, this is interesting. So I have this, you know, this slab here. It's exposed to the pressure. What about the pressure along here? Well, the gut reaction is, well, this is thin. The whole thing's thin, so it shouldn't matter, right? And then I said no in the past, okay? What's important here is the stress. The stress is the force divided by the area, which is the pressure. There's the same pressure all around. So from a theoretical point of view, it looks like you have to include the effects on the edges here. But that, you know, now that I think about it, I don't think this is correct, you know, strictly mathematically. What effect do you think it's going to have? The fact that there's a pressure on this relatively small area here. It should be negligible, I think. It should be negligible. So I need to edit this. I don't think we have to go through the trouble of shielding the edges here. I think it's going to be a negligible effect. Okay. Okay, so what's the big deal for a hydrophone? First, most important thing by far is the sensitivity. How many volts we get per Pascal? Now, what I'm going to do is we need to use this diagram. I should have just pasted it in. So I'll leave this here while we discuss this. We're going to use the equivalent circuit, right? In fact, let me do that. Okay, what's I? Thank you. Yeah, big, huge simplifications. Almost zero, right? There's probably a little bit, very small amount of current there. So this is going to be zero. That's very nice. But what about, we've got a loop here. There can be a current there. So we're going to call that I prime in this loop right here. We're going to use the usual engineering thing. And I think I better, I'm going to paste this in and draw on it. So what we want to do here, we want to recognize we've got this minus C0 and C0 here. I is equal to 0. So we call this I prime, and we assign the positive direction counterclockwise. That's the simplest way to do it, as we've discussed earlier in the course. Okay, now just to warn you, in the book, I think, I remember I had trouble figuring this out. Brian was using I, and I was thinking, oh, I thought that was 0. You know? Well, it is. This current is 0. He's using I for this, okay, which I don't. Transducer people, you know. Well, I guess all authors, right? The problem, I don't know if I told you this, but the problem with being an expert on something is when you write about it, often people can't understand what you're saying because stuff that's obvious to you is not obvious to them. So it's a problem. Okay, so we're going to call this I prime. Okay. So what's I prime is not necessarily 0, but look at this. What's the voltage drop across here? Kirchhoff's loop rule immediately tells us. No, there's a V is across here, there's a capacitor in the way. Just focus your attention on this. What's the voltage drop across here compared to the voltage drop? They cancel.
Yeah.
So the voltage, there can be no voltage across here in this case. And now that I think about it, if you want to physically understand how you can come up with this negative, that's probably, I got a feeling that's probably playing a role there. It's too simple not to be, relevant, okay? But anyway, there's no voltage drop across here. That means there's no voltage drop across here. But it can be, but there is a current, okay? Now, so we need to now look on the mechanical side, and remember, we're going to have the same essentially voltage across here, right? Because the long wavelength assumption is sound. So by symmetry, and these are the same, so by symmetry we can tie those two ends together. And we'll deal, it's convenient here, electrically you have no problem in a symmetrical situation just dealing with the total current, which is the sum of these two currents, right? It's natural to do that. By symmetry we can, like I said, we can tie these two things together. That's going to be the total current. That ought to be, the appropriate variable to deal with. But mechanically, it makes you feel funny. We're adding the two velocities, but it does have physical significance. What it is the relative velocity, and that's what's going to be important here. It's not just this velocity. You're going to double it because of the symmetry, the anti-symmetry, if you like. So it makes mechanical sense too, physical sense. So we're going to deal with that variable, and then, yeah, I really need to. Okay, so what you see there, if you look back at that circuit, I think it's better to move this 1/2 out here. We have these two Z1 impedances in parallel. We're now thinking of we're limiting the two loops. We're just thinking of it as one loop. We've got this total current U here, U1 plus U2. The two Z1 impedances are in parallel, so impedances in parallel, they add in reciprocal, so we're going to get 1/2 the impedance here. That 1/2 really, I think it's better to think of it in terms of that, and then we have that. So this allows us to solve for the velocity in terms of the force. So here's what I'm doing here. We've seen this before, and maybe a little bit differently in other cases. What we care about is the ratio, the voltage divided by the pressure, right? We're going to put everything in terms of F, and in the ratio, F is going to cancel. So, and we will need this quantity. We'll need to use this, as you'll see shortly. Now, if we look at currents, we know that I always think of this. The volt going this way is a step up. So the voltage across here is N times the number of turns times the voltage across here, right? Remember, current has to go the opposite way because power is conserved. So the current on the other side here has to be, this has to be N times this current, right? It's got to go the opposite way than the voltage. So I prime has to be in, and now, again, we think of this as a current. It's actually a velocity, and we have a dimensional ratio here. So, but this is the way I think most people do, and you're probably doing it now too. It's the ratio of the number of terms times the current, which in this case is the velocity. And the units are fine here because N has dimensions. It'll take care of that. Okay, so what's the voltage across the electrical terminal? Well, now that I know this, now that I've found I prime in terms of U, and remember we've already got U here, now I know the voltage across here. And there's a mistake here, and I can't believe I'm not catching it down. This should be positive. It's not going to really be important, but this should be positive. It's easy, and I keep checking it, and it's correct, okay? So I made a mistake here. That should be positive. Now we form the sensitivity, the open circuit sensitivity. We take this expression for the volts in terms of U. We take the pressure which is the force divided by the area, right? And we get this, and now we need the ratio of U to F. Well, we have here U in proportional to F. It cancels, and we get the constant here. And so we get, this is what we get for the open circuit sensitivity. Now, in terms of Z1 and Z2, and remember here Z1 and Z2, we've got the T's in there, that's good, they should be in there, it's thickness, where Z0 is equal to this. Remember this C here? It's not a stiffness, it's a speed of sound, the speed of waves, of longitudinal unidirectional compression and expansion waves. Now, remember we've made the assumption of low frequency, right? Sound wave, the wavelength is large. So we can make an approximation here. KT will be much less than 1 because the wavelength is large. So again, that violet, that's going to, you know, maybe all you have to do is just change this out and go to the Young's modulus speed. I don't know. I haven't thought about it, but that would certainly, that might take care of everything. I'm a little suspicious. I don't know. I just think about that. It might be that simple, but I don't know for sure. So anyway, for small kT, the tangent of a small quantity in radians becomes just that quantity in radians. This is approximately kT over 2. The sine of kT is going to be approximately kT. So we make those approximations, we get this. And now remember, kT is small because we have large wavelengths. So this is going to dominate that. So in the end, here's what we get. Well, it's not the end. Here's what we get so far. It's greatly simplified due to the long wavelength assumption. And it has, incidentally, I didn't state this, but it has some nice features here. You can see, for example, it's proportional to the thickness, which you might expect. So if you know, that's a good thing to know if you want to build this. You need to increase the sensitivity. However, we're not yet done. This is a little complicated. We can express it in a simpler way. So let's look at the ratio of Z0 to KT. We substitute, it's still got this Z0 here. So we need to plug in what Z0 is. We need to plug in this, okay? So I'm going to do that, but I'm going to look at this ratio here. It's convenient. So I plugged in what the expression for Z0. And now, do you see what's happened from here to here? We're using a fact that omega is equal to ck, where c is this speed of waves here. So that's what's happened going from here to here. And then we've gotten rid of the speed of waves in terms of the modulus here, the modulus of unilateral extension and compression. And the reason is that's related to this is the material constant. The overall compliance of the slab has this geometry. It's going to depend upon the geometrical dimensions. And we end up with the mechanical compliance here. So this has been, we can simplify this a lot. There's one more step that people make that's probably not obvious to you, but I'll tell you why. This is a mechanical quantity, right? This compliance here. Often people go to the equivalent electrical, the motional capacitance in electrical units, which is related by a square of the ratio of turns. So when you do that, here's what you finally get. This is usually the form that people will put a sensitivity in because this is dimensionless. It's convenient when you're dealing with dimensionless quantities. But ultimately, when you're dealing with this, if you actually want to get in there and really calculate, and you're going to have to probably come to grips with this, is my guess. But anyway, this is a nice way to state it. It's got this dimensionless quantity here, and some geometry, and then the ratio of the number of turns. Now, this is really a simple answer, right? And look at why did it take us so much trouble to get it? Well, you can see why. This is exact for standing waves in there. And don't worry about the fact that we're not using the right solution here because of that wavelength problem. Don't worry about that. you can notice that we treated the problem exactly until near the end here, when we finally made the approximation towards the end here. It's much easier to make the approximation in the beginning. You go back here in your circuit diagram, make the approximation here. We'll do that tomorrow in a problem. That's the way to do it. We did it the long way here. But I think that's instructive, because you'll see it's a lot easier if you make the long wavelength approximation. You want to make it as early as you can. It's a lot easier. Okay, I think that's it. Yeah, that's what I just said. Okay, anybody have any questions? Oh yeah, I don't think there'll be any problem. So let's go ahead and do the first problem. I'm confused by the numbers.
6.
6? Wow. Quarters fly by quickly. Okay, so let's look, tell you what the first problem is here. So what this is, I think this is the, okay, so remember we dealt with the length expander bar? And we showed, I didn't quite do it all, but we essentially showed that the equivalent circuit was correct. Okay, and here it is. Here's the equivalent circuit. Now I've added these, you can see I've added, conflicted with this here. We're going to look at the free case here. So this is shorted, right? A special case. But we showed, in general, even with forces, that this is the equivalent circuit. This is just an exercise to confirm that, a different way of looking at it. So what we're going to do in this problem is we're going to look at the admittance, the input electrical admittance here, and we're going to show that the electrical admittance here is identical to what we came up with when we were going through this calculation analytically. We didn't know the equivalent circuit. We were just looking at it, from the piezoelectric strain relations and Newton's laws and Kirchhoff's laws. So it's going to be confirmation of it's showing consistency here. The electrical admittance here had better be the electrical admittance that we found when we were calculating this, when we didn't know this, when we just were calculating directly. Okay, so the admittance is in parallel, just add, right? So I'm just going to add this admittance, which is 1 over the impedance, plus the admittance of, you can imagine removing the transformer here in the usual way. We need to look at the motional admittance. It's going to be the sum of the admittances. Okay. We're given this. If you look on the diagram, you'll see in terms of the basic parameters, this is the blocked capacitance. And now we need to get the motional admittance. Well, because we have symmetry, just like we were talking about before, the Z1 gets halved, and the Z2 stays there. And we get these two admittances in series, so they're going to add in reciprocal. So the motional admittance is going to be 1 over the motional impedance. And the motional impedance is the sum of the two. You'll notice I've eliminated the transformer here. That's why the n squareds are there. All right? So we can simplify this to that. And now we plug in what Z1 and Z2 are. Right? And again, it's in the diagram. In terms of Z naught. And you always, a complicated expression, you always want to look for simplification. This is not a lot of simplification. There's a little bit here, not very much. And next I'm going to substitute in what Z naught is. The expression for Z naught. That's what I've done here. This is getting kind of ugly. And I'm bringing it all under, oh yeah, you can bring it all on, wait a minute, I'm sorry, lost here. So, right, that's all I've done. I'm just going in baby steps here. Okay, so I've got this. Now, can you do something with this? Well, it turns out you can. This is with this weird half angle thing you can show. And I said readily, so I guess it's not that hard to, I haven't done this for a while. But you can prove that this is equal to, look, oh, it looks like I've simplified this. It looks, okay. To within a factor of 2, it looks like the denominator here equals that, okay? Maybe, I don't know if well, I got a 2, it's probably right, yeah. So this probably equals that. That's one of these weird half-angle identities that people never use. Everyone's familiar with the sine and cosine half-angle. You use those, you know, from the time you're undergraduates. I don't know, maybe even high school, I don't know. But this is weird, but it's true, and it's nice simplification because this is kind of messy. Now, I've also mentioned here that I've used this. I've gotten rid of, so this is, how do you simplify, so, oh yeah, okay. So I'm introducing the speed of waves here. Okay, that's how. So I've used the trigonometric identity here. I've introduced the speed of waves here to get to simplified. The next thing you want to use is you want to use we're going to get rid. We introduced the speed of wave here is just to cause some simplification. Now we're going to get rid of it. It's often what people do. You notice a lot of our expressions will not have this. We go back to more basic quantities, right? So here it is. What I'm going to do here is multiply by 1, right? And I'm going to choose 1 to be this, okay? There's different ways you can look at this. But I think the guiding point here should be, let's put this in terms of basic quantities, the wave speed. I think that would be the guiding quantity, guiding thing. And what we introduce instead is the frequency, which is the standard natural variable transduction, right? So that gets introduced here. Right. So in the end, so this is what we hit for the motional impedance. Okay, now, and of course, to be honest with you, when I first did this, I was trying to get the answer, right? This turns out to be the answer. This is what we derived analytically without any reference to an equivalent circuit, is this expression. So I was headed towards this, okay? I mean, you know, that's what anybody would do, right? We want to prove this had better be equal to this. So this is what guided me to go in that direction. And sure enough, you can see that this is the same as that. Here's C I omega C naught, or 1 over, yeah, I omega C naught, right. So remember, so the first term is this one. As you can tell by the, you know, from the expression in terms of basic quantities. And the motional admittance is that. So it agrees. That's just an exercise to show that indicates that it is that. You know, it doesn't prove that it's equivalent circuit, but what we did in a lecture in the past was more general. That was a more general proof. But this is just an exercise to prove that it's consistent. Okay, does anybody have any questions?
The KL you used here.
Wait a minute, I have a question. What's this?
It just shows where you're on the page.
Oh, okay. Sorry. Go ahead.
The KL you use in the tangent and sine expressions, is that probably where the other ones came from? In the notes?
Oh, yeah, who knows? Yeah, now this, yeah, because, okay. We first did the ring, and we beat that to death, you know, but then the next thing we did was a linked expander bar. So that's why, yeah, that must have, the expression for the thickness, I must have copied from there. Right, so here it's correct though, this is a linked expander bar. I think it's fine here. All right, any questions? Okay, so tomorrow we'll do problems, and that means there's going to be a quiz, right? That I'll send out. And you guys are working on a quiz, is that right? I made it due on Wednesday, huh? It's because you've had it for a while. If you have trouble, if you want an extra, you know, Thursday's fine. Okay? Can I have them all by the end of the day on Thursday?
Yeah.
Okay, all right. Yeah, no problem. Okay.